Every single device you own, your phone, your laptop, everything, holds its data on these teeny tiny magnetic particles. And for decades, there was this simple manufacturing trick that made it all possible. But get this, nobody really knew why it worked. So today, we're going to tell the story of how scientists used an atomic scale detective to finally crack a mystery that unlocked the future of data storage. Just stop and think about that for a second. Every photo you take, every file you save, it's all stored on materials made of particles literally smaller than a grain of sand. The huge challenge has always been, how in the world do you pack all that information in so tightly without it all just bleeding together and becoming a garbled mess? Well, the secret sauce, it turns out, is a special alloy called cobalt chromium. It's pretty much the backbone of modern hard drives. It's got these perfect magnetic properties. But for years, engineers were relying on this one manufacturing trick. You could almost call it a kind of technological superstition. It worked perfectly every time, even though nobody could actually explain the science behind it. And that right there brings us to our first chapter, the puzzle of the heated film. You've got an entire industry that depends on this manufacturing quirk that works brilliantly. But from a scientific point of view, it was a total black box. So here's the trick. When engineers would create a super thin film of this alloy, but they did it on a heated surface, its ability to store data just went through the roof. The individual magnetic bits got way sharper, and all the noise, you can think of it like magnetic static between the bits, it was cut way, way down. This let them pack more data in. But the reason heat did this? Total puzzle. Now, scientists weren't totally clueless. They had a leading theory, a usual suspect, if you will, called grain boundary segregation. The idea was pretty simple. The heat was causing the non-magnetic chromium atoms to shuffle over to the edges of these tiny crystal grains. In theory, this would build these perfect little non-magnetic walls, isolating each magnetic grain so it could reliably store one bit of data. Made sense, right? Well, there was a huge problem with this theory. When they did the math, it showed that these non-magnetic walls would only be about 0.6 nanometers thick. We're talking the width of just 2 or 3 atoms. It's impossibly small. And other research had already proven that you needed a barrier at least twice that thick to actually stop the magnetic interference. So the theory sounded good, but the numbers just didn't add up. So the old theory was basically falling apart at the seams. And this brings us to our next section, the atomic scale detective. To solve this mystery, scientists had to go beyond just theories. They needed to see what was happening, atom by atom. They needed a new kind of detective. The real problem, as the researchers themselves put it, was that the limitations in the spatial resolution of these analytical methods make it difficult to attain quantitative results. Or, to put it in simple terms, their tools just weren't powerful enough. It was like trying to solve a tiny, tiny puzzle with a big, blurry magnifying glass. They couldn't see what was really going on. So, what they needed was a new kind of detective, a high-tech one, the Atom Probe Field Ion Microscope, or APFIM for short. This is a truly remarkable machine. It's capable of building a 3D map of a material, one single atom at a time. It was the only tool on Earth powerful enough to finally crack this case. And how this thing works is, well, it's just mind-blowing. First, they take a tiny sample and sharpen it to an unbelievably fine point, just a few atoms wide at the very tip. Then, they use a powerful electric field to basically pluck off atoms from that tip, one by one. As each atom flies off, a detector figures out what it is, cobalt or chromium, and maps out exactly where it came from, building a perfect 3D model of the material's atomic structure. Okay, so with their new super microscope ready to go, the researchers could finally conduct a proper investigation. It was time for a lineup. They prepared 3 different samples, our 3 suspects, to figure out exactly what the heat was doing. Suspect number 1 was just a standard, solid chunk of the cobalt chromium alloy, a bulk sample. And as you can see, the picture from the atom probe is, well, it's totally uniform. This tells us that in its natural state, the atoms are all just randomly and evenly mixed together. This is our baseline. And the data backs this up big time. This graph is plotting the chromium concentration, and you can see it's basically just a flat line. No peaks, no valleys. This is our control group. It proves that the alloy starts out as a perfectly random mix, nothing weird going on yet. All right, suspect number 2. This was a thin film, just like in a hard drive, but it was made at room temperature, no extra heat. And the result? Exactly the same. A uniform, random mix of atoms. This was a crucial clue.
It proved that just making the material thin wasn't the answer. The heat, that had to be the magic ingredient.
So we've established our baseline, we've ruled a few things out. We know it's not the material itself, and it's not just the process of making it thin. The key, it has to be the heat. So now for the moment of truth.
This was the sample that held the answer, the one that was made using that mysterious heat trick. So what happened? What did this atomic-level detective finally see inside this critical sample? And there it is, the smoking gun. The atom probe revealed that the material had separated into two completely different phases. One phase was packed with chromium, and the other was almost pure, highly magnetic cobalt. The old theory was totally wrong. The atoms weren't just moving to the edges. The entire material was actively reorganizing itself from the ground up. The data was just undeniable. You could see it clear as day. The material had formed these cobalt-rich supermagnetic zones, and they were perfectly separated by thick non-magnetic zones that were stuffed with chromium. This process created the perfect magnetic isolation that old flawed theory could never account for. This was it. This was the answer. So the why was solved. The material was separating into two distinct phases, but that left one final nagging question. How? What was the actual physical mechanism that was making this happen? And here's the really cool conceptual leap. The old theory was static, right? It imagined atoms just kind of passively settling at the edges. But what they found was a totally dynamic process. The heat wasn't just a gentle nudge, it was giving the atoms on the surface of that growing film enough energy to actively zip around and self-organize. It's a process called surface diffusion. They weren't just settling, they were actively sorting themselves into these perfect cobalt-rich and chromium-rich zones. So we've gone on this incredible journey from a simple manufacturing puzzle all the way down to the dance of individual atoms. But what does this all mean for the technology that we're using every single day? Why does this matter? Well, let's just quickly recap the case. It all started with this long-standing mystery about heat and magnets. A new, powerful tool let them set up a controlled experiment with 3 suspects. The evidence, the smoking gun, completely debunked the old theory and revealed the true mechanism at play: dynamic phase separation. It's a classic scientific detective story. And here's the real takeaway. Understanding exactly why something works is the key to making it even better. Now that engineers understand this principle of dynamic phase separation, they can intentionally design and control materials at the atomic level. And that lets them create smaller, denser, and more reliable data storage than ever before. This is why your phone can hold thousands of photos. It really leaves you with a final thought, doesn't it? This was a huge mystery, hidden in plain sight for years, inside a material that's fundamental to our digital lives. It just makes you wonder, what other revolutionary secrets are locked away in the materials all around us, just waiting for the right tool and the right question to finally bring them to light?